These are the solutions for in-class exercise number 16, reactions of aromatic compounds. So we start here in part A. We see aluminum chloride, or Lewis acid, and an acid chloride. And that should tell us that we are, in this case, dealing with a Friedel-Crafts acylation reaction. And that means we'll end up with the substitution of this group onto our aromatic ring. Part B, based on the presence of the aluminum chloride, that would indicate that again we have a Friedel-Crafts reaction going on. In this case it's an alkylation because we have an alkyl halide as opposed to an acid chloride. But Friedel-Crafts reactions do not work well in the presence of electron withdrawing groups. With the nitro group on our aromatic ring, we have a strongly electron withdrawing group, and so this reaction is not likely to proceed. In part C, we have an halogenation, specifically chlorine. Now, in this case, we have to worry about the effects of some additional substituents. We have a pair of methyl groups. Methyl groups are ortho-para directors, and so our methyl group can initially direct to either of those positions, and it turns out both of those positions are ortho or para to both of our methyl groups. So now we have a question between the carbon I've highlighted in green and the one I've highlighted in orange. And it's more likely that our major product here is going to come from one of the carbons that's highlighted in green. That's because the other carbon, the one I have in orange, is between two other substituents, and so that position is going to be more hindered. And while it's certainly possible we could get some substitution there, we're more likely to get it at one of the other two carbons. Same thing is true in part D. We have a pair of ortho-para directors, and so we're very, very likely to see both of these positions get substituted, but the position that's between the two groups, definitely less likely. Now, in this case, we're going to have to account for two different products because our substituents are different, but it is very likely that from this nitration reaction, and we can see it's a nitration based on the reagents nitric acid, sulfuric acid, and heat, that we're going to get a mixture of these two products. Part E, we have another Friedel-Crafts alkylation. The key issue here is that we have a primary alkyl halide, and given the alkylation goes through what is essentially a carbocation type transition state, instead of just getting that pentyl chain attached to the aromatic ring, it's more likely that there will be some rearrangement taking place to form the more substituted, more stable secondary type cation, which would substitute in this way. Part F, we have another Friedel-Crafts, but amines are the other situation where Friedel-Crafts don't work well, so this is not likely to react. Part G, we have a fluorination reaction. This one's a little more complicated though, because the nitro group is a meta director. Only one of the meta positions is available, which I've highlighted in purple. The methyl group is an ortho-para director, which would be the three positions that I've highlighted in yellow. Now, whenever we have a situation like this where there's competition, the reaction is likely to be determined by the more reactive of the two groups. The nitro group is a much more strongly electron withdrawing group, and that's likely to have a bigger effect than the methyl is. So it's more likely that we would get the substitution, which xenon difluoride, our conditions for fluorination, is going to happen at the position that's influenced by the nitro group. And finally, for this group, in part H, we have a sulfonylation reaction. We're doing this with phenol. Phenol is an OP director. Since there's nothing else on this compound to influence the reaction, we are very likely going to get a mixture of the two possible products, the ortho and the para. All right, so now we can move on to our synthesis question. And you can see we've got this somewhat complex looking molecule that we want to make directly from benzene. So where do we start? Well, when I look at this, the first functional group that I know is going to be complicated to make. I know those bromines are going to be easy to put on. I can do those in a number of ways. The isopropyl group could easily go on in a Friedel-Crafts reaction. But the ether is probably going to cause me the most trouble. Now, I know I can make an ether from an alcohol. And from there, treating with strong base, followed by the correct alkyl halide, in this case bromomethane, I'll get a Williamson ether synthesis or an SN2 reaction to form the ether. The alcohol I could very likely make from a reduction of the corresponding ketone. And by doing this, I now have 4 substituents on this aromatic ring, which still means we've got some work to do. But the nice thing is, each one of these groups can be put on in a single step. The carbonyl group can go on in a single reaction with a Friedel-Crafts acylation. The bromines can go on directly with halogenation, and the isopropyl group with a Friedel-Crafts alkylation. Now, if this is going to work, I've got to do the Friedel-Crafts before I put the bromines, and especially before I put the carbonyl on. We know that Friedel-Crafts reactions don't really like electron withdrawing groups. Now, if I tried to make this compound from this precursor, what's going to happen is the bromination is going to be influenced by the substituents that are there. The carbonyl group is a meta-director because it's an electron withdrawing group. The isopropyl group, as an electron donating group, is an ortho-para director. Well, because of the substitution, the 2 carbons highlighted in yellow are ortho to the isopropyl group, meta to the carbonyl, and they're exactly where we want the bromines. So if we do 2 halogenations, we'll get the bromines in both of those positions. Now we just need to get those 2 carbon groups on. We said we can do both of these as Friedel crafts. But I would have to do the carbonyl group second. Carbonyl group is an electron withdrawing group, and that would prevent any subsequent Friedel crafts. So if I start doing this Friedel crafts with 2-chloropropane, I'll get the isopropyl group. The isopropyl group is an ortho para director, which means I'm going to get substitution at each of these positions. It may end up working out that because the isopropyl group is slightly bulky, that it pushes things away from the ortho positions. Odds are, though, I'm probably going to get a mixture of the ortho and para products, and I'll just move forward with the para one. But that sequence of Friedel-Crafts reactions is going to first put my isopropyl group on, and then give me the acyl group para where I need it. All right, question 3, we're looking for a mechanism here for this Friedel-Crafts. We know that a Friedel-Crafts will begin by the carbon-chlorine bond adding into the Lewis acid. And this gives us a carbocation-like species, which, if it shifts over a carbon, we get the more stable secondary type carbocation. Once we do that, our aromatic ring can attack, causing that bond to completely break. And then the AlCl4 will remove the hydrogen to regain aromaticity. Our final question looks at the cyano group, and we're asking if we had a cyano group already on our aromatic ring, where would we expect that to direct new substituents? And this is something that we can always look at through resonance. So if we look at our starting material, what kind of resonance structures can we draw? So we can shift these pi electrons up into the nitrile. This puts a negative charge on nitrogen and a positive charge in the aromatic ring. We can then continue to shift these electrons around. And we'll see that positive charge continue to shift around the ring as well. Finally, we can do this one more time. To get yet another resonance structure. What each of these resonance structures are showing us is that because of the nitrile group, we have positive character at both of the ortho positions as well as the para positions. That means those positions will be less reactive, they're deactivated, and the nitrile group, just like any other electron withdrawing group, will deactivate the aromatic ring, but further, it will push new substituents to the meta position.